Hi everyone, my name is Elizabeth. This is my Module 4 assignment, the movement of macromolecules flowchart and video presentation. So, here's my name, 626. Let's get started. Among the vital processes of the cell includes the production and movement of macromolecules. Macromolecules are vital for fueling the many processes and cellular work that happen inside the cell. Hi everyone. So the first macromolecule that I will discuss is a lipid, specifically a lipid known as cholesterol. Cholesterol is a component of the cell membrane of all cells and it is actually produced by every cell in the body. However, this production only accounts for a small amount of the total. The majority of cholesterol synthesis occurs in the liver and the hepatic cytoplasm. Craig, 2023. The process begins in the cytoplasm with 3 molecules of coenzyme A and ends with the condensation of 2-FPP farnesyl pyrophosphate in order to form squalene. This squalene is converted into cholesterol in the endoplasmic reticulum. She et al. 2022. Once cholesterol is produced in the endoplasmic reticulum, it is exported to the plasma membrane and to some organelles. Typically using transport vesicles, they often couple the transport of cholesterol with other lipid products like sphingolipids. She et al. 2022. Some of the organelles that receive cholesterol include the mitochondria and lysosomes, as well as the Golgi apparatus to take part in the trans-Golgi network, to be sorted with other lipids. She et al. 22. Once it is synthesized, cholesterol may be used as a precursor to bile acids. Cholesterol is also involved in vitamin D synthesis and steroid production. It contributes to the cell membrane by creating both fluidity and structural support. Craig, 2023. Cholesterol is a shared precursor of all steroid hormones. This includes androgens, aldosterone, and cortisol, the sex hormones, glucocorticoids, and mineral corticoids. The way that cholesterol is transported in the body is via lipoproteins, specifically apolipoproteins. You've likely heard the terms good and bad cholesterol at some point. The bad cholesterol is used to describe LDL, which is also known as low-density lipoprotein. LDL receptors bind to cholesterol and are used to transport most cholesterol through the plasma and into the peripheral target tissues. Luke et al. 1989. Following receptor-mediated endocytosis, the cholesterol is then used to form cell membranes and synthesize hormones, bile acids, and more. The deposited cholesterol that was brought to the peripheral tissues by LDL is absorbed by the good cholesterol, also known as HDL or high-density lipoprotein, and turned back into LDL. This LDL is then broken down by the liver and excreted as bile. Luck et al. 1989. So just to summarize the path of cholesterol within the cell, cholesterol is first synthesized in the cytoplasm of hepatocytes, which are in the liver. The second step is synthesis is finished in the smooth endoplasmic reticulum. It is then loaded into transport vesicles. The next step is it's exported to lysosomes, mitochondria, and or the Golgi, or to the plasma membrane, just depending on where it's needed. And then the final step is that it joins the plasma membrane or is involved in the cellular processes or the TGN, aka trans-Golgi network. The second macromolecule that I'll be discussing in this video is insulin. Insulin is known as a secretory protein, meaning that it is secreted by the cell. This peptide hormone works in conjunction with glucagon to maintain euglycemia in the body. Venugopal, 2023. Depending on the blood glucose levels, either insulin or glucagon will be excreted in response. Insulin synthesis begins in the beta cells of the pancreas and the islets of Langerhans, specifically from the ribosomes housed in the rough endoplasmic reticulum, which produce its precursor proinsulin. Galizzi and DiCarlo, 2022. At the ribosome, proinsulin is folded and its disulfide bonds are manipulated. To bring proinsulin from the rough ER to the Golgi apparatus, transport vesicles are utilized. Galizzi and DiCarlo, 2022. Within the Golgi apparatus, the proinsulin undergoes a chain of reactions with multiple proteases to become proper insulin. When the presence of glucose is detected, the insulin is excreted via exocytosis using secretory vesicles to outside of the beta cell. Galizzi and DiCarlo, 2022. Once the insulin is secreted into the hepatic portal veins, it binds to somatic cells, including skeletal muscle, liver, and adipose tissues, using a glycoprotein receptor, also known as INSR, on the cell surface. There are two subunits that comprise this INSR receptor. There's an alpha subunit that binds the insulin and a beta subunit, Con 1985. This beta subunit is a tyrosine protein kinase that becomes stimulated by the insulin. This signals GLUT4, which is also known as insulin-regulated glucose transporter, to come to the cell surface. This also signals for glycogen to be produced in the smooth endoplasmic reticulum. GLUT4 is housed in a membrane-bound vesicle and binds with the cell membrane to release the transporter. Howe and Pessin, 2007. GLUT4 then begins to bring glucose through the transporter using facilitated diffusion, Richter and Hargreaves, 2013. The glucose is taken into the cytoplasm to be processed via glycolysis. IDE, otherwise known as insulin-degrading enzyme, is responsible for breaking down insulin into inactive fragments by engulfing it. So just to reiterate the path of insulin within the cell. The first step, it's synthesized in the beta cells of the pancreas, specifically within the islets of Langerhans, in the ribosomes of the rough endoplasmic reticulum. From there, it goes into transport vesicles, and it is transported from the rough ER to the Golgi apparatus. From there, it's sorted, and then it is placed into secretory vesicles. And then the final step is the secretory vesicles merge with the cell membrane to be exocytosed. The third and final macromolecule I will be discussing is actin. Actin is considered a cytoskeletal protein, and it is the most abundant protein found in eukaryotic cells. Dominguez and Holmes, 2011. Actin has two forms, a monomeric form, also known as globular actin or G-actin, that binds to other monomers, and a filamentous double helical form that occurs when actin monomers polymerize. This is known as filamentous actin or F-actin, Cooper, 2000. Actin is involved in numerous cell functions, from cytoskeletal support to assisting with mitosis, while filamentous actin works with myosin to produce muscle contraction. Actin, like all proteins, is synthesized by ribosomes. In particular, actin is made by the free ribosomes in the cytosol of the cell. Since actin is synthesized by free ribosomes rather than the rough ER, it is not automatically enveloped in a transport vesicle from the endomembrane system. It must be sent to the Golgi apparatus to be processed and placed into transport vesicles in order to reach its final destination within the cell. The Golgi apparatus itself is supported by a network of cytoskeletal elements, including actin, Ravichandran, 2020. The assembly and disassembly of actin filaments is regulated by actin-binding proteins. Actin comprises cytoskeletal support, polymerizing to form filaments to assist in muscle contraction, cell division during mitosis, transport within the cell, and many more functions. To summarize the path of actin within the cell, it is synthesized in the free ribosomes of the cytoplasm. It is loaded in transport vesicles, and/or it's acted upon by actin-binding proteins. It's sent to the Golgi apparatus for transport, and then its final destination can vary. It can go to the cytoskeleton in globular or filamentous forms. It can join cell transport networks, organelle support, and many, many, many more functions. Thanks for watching my project.